Hello everyone, this is Dr. Alok Agarwal and I welcome you all on our next lecture on course Fluid Mechanics having course code ME404. So in this lecture we will start our unit 5, that is boundary layer theory and compressible flow. In that first we will start with the introduction part. See, in this we will consider a solid body inside a medium where fluid is flowing. Generally, we consider that fluid is water. You can take any other fluid as well. And we will see here that there is a solid body and the fluid is flowing with a velocity u here from left to right. So when a real fluid is flowing over a solid body or a solid wall, what will happen? The fluid particles will try to adhere to this solid body. And why it is so? Because of no slip boundary condition phenomenon. So the fluid passing through the solid body, it will try to attain the velocity of this solid body. If the solid body is at rest, the fluid will be at rest. And if the solid body is moving with certain velocity, the fluid will attain that velocity. Okay. So what does it mean? That fluid, the first layer of fluid particle which come in contact with this solid body will try to adhere with this body. This means that I have already told that the fluid of velocity of fluid close to the boundary will be same as that of the boundary. If the body is stationary, the fluid velocity will be 0. In this case, we will consider that the velocity of this body is stationary. Okay. Again, as we move away from the boundary, this solid boundary, when we move away from it in a perpendicular direction, what will happen? The velocity increases. The velocity slowly increases from 0 and it will reach at a point where the velocity of the fluid will again come back to the original velocity, that is free stream velocity u. What does it mean? It means that the velocity varies from 0 velocity at the boundary of the solid body and it will attain velocity u at a certain distance from the solid body. So there exists a velocity gradient which is given by du by dy. This velocity variation from 0 to free stream velocity occur in a very narrow region, okay? This narrow region is called boundary layer and the theory which deals with this region is called boundary layer theory. So in this unit, we have to study this part only where the velocity gradient exists. After this layer, there will be no velocity gradient and can be seen from the figure that the velocity of each layer is equal to the free stream velocity, whereas the portion near the solid body, the velocity varies from 0 to certain free stream velocity. Okay. Now, according to boundary layer theory, the fluid which is at the neighborhood of the solid boundary is divided into two regions. First region is a very thin layer of fluid, which is we called it as a boundary layer, which is at the immediate neighborhood of the solid boundary, where the velocity varies from 0 to the free stream velocity. In this region, there is a velocity gradient and hence there is a shear stress, where the shear stress in this region can be calculated by Newton's law of viscosity that we have already learned in unit 1. Again, the second region is away from this region where the velocity gradient exists. Here in this region, there is no velocity gradient, which is outside the boundary layer, where the velocity remains equal. The different layer have showing the same velocity, hence velocity gradient is 0 here. Okay, so these are the two regions. The region 1 is where velocity gradient exists and region 2 is where velocity gradient does not exist. And the line which differentiate these two regions, we called it as a boundary layer. Let us consider a thin plate over which the fluid will flow having a free stream velocity u. So we will discuss this various definition associated with the boundary layer. That is, what is laminar boundary layer, turbulent boundary layer, laminar sublayer. We will going to see each in detail. So let us consider a thin plate AB. The boundary layer region begins at the leading edge. If the fluid is flowing from left to right, point A is called leading edge and point D is called trailing edge. So the boundary layer region begins at the sharp leading edge. At the downstream of the leading edge, when we move from A to D, the boundary layer region increases. Because why it is so? Because the fluid which is retarded with the influence of this boundary will further retard. Okay, because why? Because Here, the influence of this plate will be more because the fluid is already retarded, means its velocity is already dropped, and when it comes with more uh, plate, its velocity will further retard, and we called it as a growth of boundary layer. Here we can see that the boundary layer thickness increases. This is the thickness of boundary layer, and when we move towards the plate, along the plate from leading to trailing edge, the thickness of the boundary layer increases. Again, near the leading edge where the thickness is small, here the thickness is small. Here the flow inside this boundary layer is laminar, though the fluid coming from far having a turbulent behavior. Okay, this layer of fluid is said to be laminar boundary layer and is shown by AE. AE is showing the laminar boundary layer. In this region, the fluid which is moving having a velocity very low, and it is called laminar flow, and that's why this layer is called laminar boundary layer. Again, the length of the plate from the leading edge up to which the boundary layer is laminar, we called it as a laminar zone. So if AE is the laminar boundary layer, we will drop perpendicular from E to the plate, we will get point B, and this AB, we can say that it is a laminar zone. Above this portion, the fluid which is inside the boundary layer showing the laminar behavior. And how to calculate this laminar zone? See, the distance B from the leading edge means AB will be calculated with the help of Reynolds number, as we know that the fluid flowing over the plate, if the Reynolds number is less than 5 into 10 to the power 5, we can say that the flow is laminar, and if the Reynolds number is more than 5 into 10 to the power 5, we call it as a turbulent flow. So with this formula, we can calculate the value of x. First, we will consider that AB be x, and if we want to calculate x, we have to keep Reynolds number 5 into 10 to the power 5. We have to put u, free stream velocity. This nu is viscosity. It can also be written as rho u x by mu, where nu can be converted into dynamic viscosity and density. So both the formulas are correct. Okay. So if from this value we can calculate the value of x, and with the help of this x we can locate point B, and we can say that up to this point the fluid will show laminar behavior, that is, it is laminar zone. Again, if the length of the plate is more than this value of x, okay, then we can say that the thickness of the boundary layer will go on increasing in the downstream side. Okay. Later, the laminar boundary layer become unstable. After this point, the laminar boundary layer become unstable, and the motion of fluid within this boundary layer become irregular, and we can say that the flow is changing its behavior from laminar to turbulent, and this changing behavior occur between point B to C, and we called it as a transition zone. Okay. This short length of the boundary layer, where the laminar flow changes behavior to turbulent, is called transition zone, and it is EF. Further downstream fluid move, the thickness of boundary layer grow further, and we call it as a turbulent boundary layer, which is shown by FG, and this CD is turbulent zone. But we can see that a region in the turbulent layer adjacent to the solid boundary, C, this CD is turbulent zone, but very near to this solid body CD, there exists a laminar sublayer. Laminar sublayer means where the influence of viscosity is high, and because of that high effect of viscosity, the very small portion near this plate will show laminar behavior. Even this is inside the turbulent zone. So we called it as a laminar sublayer. Okay, here the velocity distribution again follow the parabolic path, and the velocity gradient is considered as a constant. Okay, thank you. And in next class, we will see the boundary layer thickness. Thank you very much.